So first I had to make a question, who knows about PRACE? So half of you. So I have one slide about PRACE. So I think that should be enough. So my area of experience is the networking and the security. So what I'm now doing is explain to you the PRACE network and the monitoring issues we have in PRACE. So since the first days, PRACE has offered an internal network connecting the different supercomputer systems by a dedicated infrastructure. And in the next slides, I will show you how we set up this and why we have set up this. So the session will provide a detailed overview about the current network status, the new infrastructure we are just migrating to, and the transition path, how we do this. Details of monitoring of the infrastructure and setting up of a local environment for the monitoring, and at the end, some details about the PRACE IT security and security policies. That's not going into technical details, it's really an overview of administrative and organizational things. So the original idea for the network, why did we need a network for the supercomputers? Supercomputers stand for their own, they don't need external resources only, but they need the data to get in. And the idea in 2004 was already the EU project DISA to connect several tier 1 systems throughout Europe. Because we said there are some countries which really can spend money for a supercomputer, but there are other countries in Europe where researchers don't have these facilities. So setting up supercomputers, providing them for the whole research in Europe would make sense. And all these days, all the systems have been similar IBM systems. So the idea was, why not connect them by a high-speed network? That if one of the systems is really highly used, and there are a lot of additional jobs, why not send it to another supercomputer system and compute it there? The problem here is, of course, that the data isn't at the other supercomputer system. And there was the idea, because it's all the same systems, we can reroute jobs to the other system and use the data via a global parallel file system. And this time, IBM provided a shared file system with the multi-cluster GPLS, and we tried to set this up. And we started with a 1 gigabit connection, and later on we came to 10 gigabit. So the network requirements, of course, simultaneous reservation of networking, processor, and storage resources leads to increased complexity. You need the supercomputer resources, and at the same time, you also need access to the data, which may be on another system because of this distributed environment. Software interfaces and accounting procedures to request such ad hoc to establish communication paths can be developed. Until then, unique bandwidth on demand. For example, this is today available, but not in the way I would like to have it. For example, I would say I would like to have a 10 gigabit connectivity on Monday morning at 8 o'clock because I need that in network. That's not really available. You have it in principle, but a lot of details are not really clear how to solve it. For example, who is allowed to reserve those resources throughout Europe? Who can spend the money? Who is allowed to take this money and really to reserve? So what we saw, what we need is a dedicated network for our infrastructure. That was what we set up. Additional environment is a dedicated environment without bottleneck identification because of easier reproducibility. If you have a problem, you really know where you have to look for. If you have a shared environment, there may be other users which have used the network. You cannot get the situation you have with your problem once again to test your various problem. And of course, much enhanced IT security because there are no packets from others. You really know what is going on in your network. So one more comment to the DISA consortium. It was a project, as I said, started in 2004, and I think it was going until end of mid of 2009. Connected Tier 1 systems, so national systems, and you see here the it was English, FZA, RCP, Genica, EPCC, CSC, Zara, and ECN. Most of them are also part of the PRACE now. The only one which is this one. So, what was the idea? Just take the open networks of the DISA project into PRACE. And now my slide about PRACE. It's really an overview slide so that you know what I'm talking about. PRACE is the European HPC research infrastructure. So the idea was, so we have national systems which can be used by researchers. There is a problem, there are problems which are so huge that they cannot be solved on a national supercomputer. It's too expensive. So why not get all the money from the European partners together and buy one big supercomputer, maybe more of them, but some only, which are really big and can really compute the huge problems. So that was the idea of PRACE, enabling world-class science through large-scale simulations, providing HPC services for leading-edge capability systems, and those systems are really systems which are comparable to the big supercomputer systems in the US, Japan, China, and so on. With China, we cannot compete. It's too big, but in principle, we want to be in the upper edge, really provide very good resources. We wanted to operate it as a single entity to give access to world-class supercomputers, extract, train, and retain competencies, lead the integration of a highly effective HPC ecosystem, and offering its resources through a single and fair pan-European peer review process with academia and industry. So you just have to ask for supercomputer resources, and there is a committee which looks into your proposal and says, yes, let's was to be computed here. The supercomputers are not only sold, there are 200,000 CPUs, just use it. Those supercomputers are very expensive and they are special, so only applications really fit into the system should get computing resources. That's why we have this regulation.
Yes, politics shouldn't enter into this, right? These politics shouldn't enter into the regulation. I have a question for Cyprus.
Yes, it's really it's a scientific committee which looks into the other resources. So it should be political, but of course anything is political.
I'll leave the question for later.
Yes.
And it's very political, but
yes. So maybe I cannot answer it, as I said, the networking is yes, okay, we'll see. So crazy numbers, currently it's 25 members, 400 million total funded by hosting members for PRACE systems and operations. 10.2 billion core hours awarded during this period from 2012 to 394 projects from 38 countries, and you see already it's 25 members, and all these members are one from 25 countries, it's less countries. 25 prototypes of new architecture technologies evaluated, 100 of scientific applications enabled, 50 companies have been supported, and 60 best practice guides and more than 200 white papers have been published. Only when we have overview of this project. So, now coming to the PRACE network. I think all of you know the GEON network, which is all these ANRADs and all these research centers in Europe, and it's at the end it's the fiber network where which GEON operates. And if we have a more detailed view, it's not only fibers, it's wavelengths of these fibers which are used. And what we did was just asking for some of those wavelengths, setting it up as switch or layer 2, layer 3 router in Frankfurt, using some of those wavelengths, putting switches or routers at the end of those, and connecting the supercomputers. At the end, we didn't connect the sites, we connected some small subnets of the sites where the resources are in. So the grid FTP service, the supercomputers themselves, some monitoring system, but in principle only the resources which are part of PRACE. So that is why it's a dedicated network. We have a net of trust. Here can be security. That we say, for example, HLRS only connects merely systems which are part of PRACE. Not other systems of HLRS can use this network. So it's really dedicated. Only packets for PRACE goes with this infrastructure. So at the end, that's what we implemented. And you see here, it's not the clear state. The red line are those wavelengths. Sometimes, for example, France, they end at Renater, the emblem of France, and then have Ethernet connection to the different partners. Here, we saw after some years that not everyone needs 10 gigabit. Maybe we have an IPsec gateway with 1 gigabit connections, so that you get into this and can connect to the system. So at the end, it's again secure to connect. You know exactly who is connecting here, and it's encrypted. So the net of trust is realized. So afterwards, we saw there are new services which GEON provides. So Bulgaria and Greece connected with the 1 gigabit GEON. We have 2 VPN service. So another step in our infrastructure where we went, and at the end, this is something similar to that what we would set up in the unit. So the dedicated PRACE network characteristics, it's structured as a star topology, made of trust, security policy, it connects small IP networks of PRACE partners where only PRACE systems are connected to, links to traffic are encrypted and are dedicated to PRACE traffic only. So the star topology has a lot of advantages, but also disadvantages. There's a central switch. If it goes down, nothing happens anymore.
No redundancy?
No redundancy. We did this because we said all these supercomputer systems are systems which can work alone. If the switch really breaks down, we can reset it within 4 hours. We go to Frankfurt, set up a new one, and it will work again. If the link goes down, okay, we have to see how long the algorithm takes to set up the link again, but the system as its own can work. So it just doesn't compute jobs which need connectivity with others. So it's not a real problem. And the switch didn't go down since 2004. And it's the same switch.
That's because there's no redundancy. They cause problems.
Yes, so it was an easy solution, but as I said, it never in the whole 13 years until the setting up of the switch, we had 3 times that the port went down. So we just changed the port and
And inside the switch, is that your supervisor or something, or that's also?
yes. No, of course, the switch is it's Cisco 6509. I say it's good quality. And we had 4 hours updated with something equivalent within 4 hours in the hardware problems. So that's a disadvantage. Most sites connected with 10 gigabit wavelength, then it's very good. You can have high speed throughput. Several sites connected with 1 gigabit shared IPsec GRR tunnels. That's good or not, but it depends how much bandwidth you need. If you have a 1 gigabit connectivity and you have to share it with the others, it depends. Maybe you get the whole 1 gigabit if you have fast encryption routers. If you just get a time slot where a lot of others also communicate, you don't have much throughput, but you have connectivity. Okay, that's the advantages and disadvantages. So in the meantime, GEON provided a new service, the multi-domain virtual private network service. And what does it provide? It provides private high bandwidth international connectivity for research and education partners, and provides provides to the combined Android and Xeon network, building a true multi-domain MPLS VPN. At the end, it's what we need on a virtualized basis. It's the same infrastructure as the normal IP traffic for academic users. At the end, it's the same links, it's the same routers which they use, but it's virtualized. It's designed to be robust, highly scalable, and secure. I should say that it's from the slides from Joe. I do a little promotion. So, but it describes exactly what they want to provide. Because of logical traffic transformation, firewalls are non-essential, enabling high throughput performance. So it's a dedicated network. You don't need a firewall if you trust the other side. If you don't trust them,
Engine. You have to trust the end as well.
yes,
Not to make
of course,
mistakes. Not to make mistakes, not just.
Not only mistakes, but we have to trust the staff members of your home. Of course, they can look into this, into the.
Obviously, also if they make a mistake, it can also cause the. There doesn't have to be someone hostile here. If someone is not careful, it can
Yes.
also.
But that's the same for your normal IP traffic. It's the same infrastructure. So and of course you have to trust, but you also have to trust that this is a dedicated network. It's a wavelength, and I don't put all these cables into the switches of Geon. They do that. So they could put in a prism and also with the data. But you have to trust.
No, but this isn't numbers. This isn't wavelength.
But there's a difference.
It's IP based, right?
Yes, but there's a difference.
When you separate the opticals, which has a different wavelength, there's less chance of things going to the wrong place.
No, you just put the fiber out, put in the prism, put in the fiber again, and they can read anything if they want.
Yes, if there's a
So you have to trust.
Yeah.
You can encrypt your traffic. That's not a problem. And they can read. They can do what they want. But they provided connectivity, a direct connectivity, and if they do anything right, no one can interfere packets from outside. And that's what we want. So, seamless infrastructure, only configuration of end-user connections needs each type of delivery much shorter. So if we have a dedicated wavelengths, we really had to set up a new link, the fiber, and all these things was dedicated, at least at the end, at the last mile, and so on. Here, it's only a configuration issue, and it's done much faster. So when a site wanted to connect to PRACE, it took 4 hours, 3 months, depending on the site. Here it takes, let's say 1 hour. 1 hour configuration, and send emails, and he's approved to connect, please connect him, and someone has to configure and it's working. So, intermediate networks are transparent for end users. The typical scenario Jean describes, that's exactly what the PRACE infrastructure is. An international corporation where a project wants to connect a number of sites from different physical locations to create a collaborative infrastructure as if they were in the same physical location, same level of security, as all the sites would be in the same location. It's exactly what we want, and it describes the PRACE infrastructure. Service is implemented by over 100 European Emirates, so in principle, you can have it everywhere. Delivered to end users over a service demarcation point at the edge of the Emirates or regional network, the Emirates router, where the traffic is separated. The kind of delivery to the end users depends on the Emirates. There are different kinds how to get set up this, and the Emirate decides what is the technical realization at their side. And each Emirate determines their local MDVPN pricing policy. That may be a problem. So we always have a problem if we ask if we would like to be connected to the PRACE network, how much does it cost? And it really depends on the Emirate. We never had contracts with Jean. We don't know what Jean gets out of this. We only have contracts with the Emirates. If the Emirates says Jean is so expensive, we have to take the high price. we have to accept this. Of course, we also impact this So the future PRACE dedicated network. The infrastructure will be set up on the combined Geom Emirates backbone, providing the VPN between the PRACE partners who use this MDVPN service in the future. All partners will be connected by VNet through their normal Emirate connection to this PRACE VPN. And then Emirates, where MDVPN solutions are not available, I said half of the Emirates already have it. You can connect via MDVPN proxy provided by Geom. At the end, you use an IPsec connection to Geom, and then you get into this. That's possible. So then there are two possibilities at the end how you can set up logically, let's say. So the first one is you use your normal internet connection, just sharing this connection and having here at the end of the second delay. As the second one is you say, no, I don't want to share it, I want to set up an additional link. Of course, that's more expensive, but you can do that also. For example, to say, I only have here a small bandwidth and don't want to share this PRACE because my users, which are not related to PRACE, should be affected, then you put that out this way. At the end, as you see, it's the same outcome. So the question of costs and benefits.
This goes together with the PRACE 5.3 project?
Basically.
This goes together with the PRACE 5.3 project? With the
yes and no. We started to evaluate this in 2014, and it took a lot of time to get all the partners convinced that made sense, and it took much more time to get all the prices for this. And at the end, the decision was, if it becomes much cheaper, why should we do that? Except we would say we really need the dedicated links because we need the 10 gigabit. But it isn't the case, we don't need 10 gigabit. We need the connectivity, we need the security, and if you don't have the capacity here, you can do it this way. So at the end of 2016, the management board of PRACE decided, yes, we go this way. And since then, we are migrating. And the end of migration should be end of this week. So let me say a little bit more than half of the PRACE partners have migrated. So I hope a lot of them do it this week. And if they don't do it next week, they don't have connectivity. But as I say, that's not really a problem. They can do the local things until they get Good. Migrating is ongoing. Phase 1, Jülich, CSCS, Tunica, and BSC have been connected in advance as a test case. In the meantime of the project, we also there came up a new European project, the Human Brain Project. I don't know if you know about that. The medical project researching on the brain with two aspects. One is to know how the brain is working. To manage diseases. And the other one is, if you know how the brain works, maybe we can construct supercomputers with so low energy consumption. So it's a project over 10 years, and the main supercomputing partners in this project are these four, and those are also PRACE partners, so why not use the PRACE network also? So, and we said HPP will start with this network and we'll test it. We set up additional links for that. So we have the PRACE connectivity and additionally this connectivity to VPN and tested that. Phase 2 connectivity between the PRACE VPN and the dedicated network has been established. We have set up 10 gigabit links so that the partners which migrate already can reach the old partners via the script. In phase 3, further PRACE partners migrated, NIRF and CSC. In phase 4, so this week it is assumed that remaining partners will migrate to PRACE VPN. We have already 2 or 3 which have migrated since I made the slides. So, phase 4, beginning of May, all dedicated router and 500 will be decommissioned. and I have pictured this in the next slide a little bit. First, the PRACE VPN characteristics, the PRACE network structure. The structure is a full mesh VPN. You can reach each other via this links. Maybe it's not really anyone to anyone, but logically it's anyone to anyone. Of course, we use this PRACE geo infrastructure where maybe the links are shared. So the net of trust security policy is to connect small IP PRACE partners where only PRACE systems are connected to. There's no change, it's only going from physically to virtual. No default encryption, but dedicated to PRACE traffic. The VPN technology, the links between sites are provided by Android and beyond, fully transparent. It's a layer 3 VPN, most sites use a connection to the Android shared with normal IP traffic, but use different VLANs. Connection speed depends on partner, can be up to 100 gigabit, for example, CSCS has 100 gigabit connectivity to their switch Android, and they can use this. Other partners may have only 1 gigabit. Share this, it depends what they will need. So what we have to see in the future, for example, this switch partner which sends so much traffic to a 1 gigabit partner that the shared link cannot be used anymore. I don't think that this will come up, but that could be we have to see in the future. And then we may have to press down the PRACE traffic. We can do that on the configuration base.
Sarah in the group. Sarah sending to start in Israel. Why? Because there was just a much bigger links.
Well, we have to see if this happens, but I don't think so. Especially I think so because the partners don't optimize their network. So you all know if you have a 1 gigabit link and you set up an FTP or an SSH SCP connection, what do you get out? 20, 30, 40 megabytes? Because these systems are optimized for networks. They could get 1 gigabit, but they don't. So no GM and the DPF access via local Android possible. We can use this GM. So that's the sketch what we have. That's a kill network. We set up this PRACE VPN, realized the own infrastructure. We connected some sites additionally to the normal links. Just see here it is. Here should be a red line. So they have additionally then PRACE BTP announcements. So that we get the connectivity between the old and the new infrastructure. Each partner advertises local network input via BTP to the PRACE VPN, so everyone knows where the other partners are. Any other partner has to accept advertised routes. Local access may be installed on English routers, firewalls, if you require IT security in a set. Because of the net of trust, you don't need firewalls, but if you say you need it, of course you can install a firewall on your side. The old central router knows is via BGP. The routes do not migrate to partners during migration phase. So at the end, we have this. We have the connectivity here between the old infrastructure and the new one. And for example, let's say CaSToRC sends packets in here, and reach via this with some of the other partners. And you see here now in this slide, the new the partners which migrated already don't have a link to the old infrastructure anymore. They don't need it because they can access the old infrastructure as it's there. And that's the current situation. So hopefully next week it looks like this. No one needs anymore the old infrastructure, and then we can introduce the old infrastructure. Hopefully. So that's the migration plan. The status of migration it's done with BSC, CSC, CSCS, FCJ, and IIF. CEA just connected yesterday. Idris told me they have migrated. I have to check this. This we will do after the session. They will be on next Wednesday, so they will have maybe 1 day not no connection. And the others we have to see, they say no actual info, means they contact the advance, and I don't know the steps. And those are sites which don't need any connection to the PRACE network. They say we have special jobs only on our supercomputer, which doesn't interfere with any other PRACE partner when we don't need it. So our users which compute on our systems just connect from the outside to the system. So that's also a possibility. Connectivity. So if they want to have connectivity, they must be able to normal internet. Of course, the supercomputers also have connection to normal internet, but only connected to PRACE. So at the end, it should look like this. Anyone is connected to the PRACE VPN. It's a virtual connection, so no links. We see no physical links.
Yeah.
This?
Cloud is a good password.
So a little bit about network monitoring. We have a special web server where all the information concerning the you cannot just if you want to try, you cannot access it because it's accessible by special IP addresses only. So because we say in 4 days, we shouldn't provide this information, how much is transferred of the different links and how much is the situation of the network to the whole world, only to the partners, and that's an IP tables list where I include all the partners. When they told me we need access to this IP address range, then it's possible. So a lot of network information, how it is connected. Some of them are outdated. I want to update this when we have the new infrastructure. Then we will update this so that everything is correct. Here we have the monitoring part. We have PRACE partition reachability, the performance test matrix. At the end, we do hyperpath transmission with all the partners. We have a round trip delay matrix here. Performance test time schedules, so that not everyone sends at the same time the hyperpath. That doesn't make sense. Contact information, trace route information, and so on. I will go into a little bit more detail.
You don't want personal?
I tried it, and at the end, the problem with personal is that some partners don't allow to have systems inside their environment which is administrated by their staff. That would mean that every partner would have someone who's who knows about the personal. So we discussed it a lot. At the end, I set up the system before personal was available. At the end, it's the same.
Yeah.
Personal is using the difference is that the personal starts the server when it uses the remote server, when it needs to test. And with this setup, the server is running. You have to set up this iPhone server and waits the overall connections. Okay? If you look at partition reachability, it's simple. It's just having a list of systems we test and we have a network monitoring station in Unity, which just pings all these sites. So at the end, it's the connectivity from Unity to the network would fail anything to progress. But okay, that's a special case, and then we know it's a connectivity. Here, for example, in this at this time, the CEA wasn't reachable, and CSA wasn't reachable, and RCG wasn't reachable. RCG is the kill state, and they disconnected from the dedicated network and have not migrated to the new one, so they cannot be reachable by others. So you just see it's a computer reachable by the network. Of course, you can click here to get more information. How long it has been not reachable and so on. Information about how much is the round trip time. So next one is iCloud matrix. At the end, you see it looks a lot of red. It should be green anywhere. The problem here is also it's not actual because a lot of the systems have changed. They must set up a new iCloud server. I didn't look into this because I said I will do it after the migration. Then I really will stress that everyone who has to set up it should set up an iCloud server. And I assume that not every one of these systems will be needed. We have to discuss who really wants to be in this table. I want to have it green, and if someone says I don't want to install it, it shouldn't be in the list. It doesn't make sense to always say it's that. So my initial idea was really to have every system in this list. Every system which is a production system. But there are different reasons why it's not possible. Okay. One information more you see here, I assume you cannot see it from far. It's three for every partner. It's three numbers. It's TCP throughput, UDP throughput, and packets lost, percent packets lost. And if you see, for example, if you have 10 gigabit connection and only get 50 megabit out of it, it's not optimized. Something has to be tuned. And the problem here is really that it's not easy to optimize because iCurve works different dependent on the operating system. You really have to stress a lot of parameters. I will get into this later. To adjust buffers, to see how much packet, how big the packet has to be to send to really get optimized numbers. And that's really the problem we network the space with the data. If you set up an application transferring data, it doesn't know about the underneath network. It's not optimized for the network. It's just assuming default behavior. And that's why you don't only get 20 megabit out of an FTP. So you have 10 gigabit connection.
Does the VPN also play a part in this? Or not?
Does it begin?
Does the VPN also play a part in these,
in this
migration for throughput for
of course, because it's shared.
Not only
If you have a
shared,
shared-
the maximum
just put the fact that is packet sizes.
Yes, of course.
and fragmentation.
Yes.
That is also.
So if you optimize for the sites that don't have VPN, the sites have.
There are a lot of parameters where you can play with. Of course, this VPN itself is also one of the parameters. We have to talk to John that they like Jumbo frames and all these things which have to be optimized, of course. Okay, trace network monitoring setup. Special software has to be installed on a monitoring node at each partner site. It can be a login node, compute node, gateway node, or any other kind of node with a HPC system which has an interface with the PRACE node and subnet. So I said it must not be the supercomputer which does the iCloud. It could also be a FTP server or a special server. Doesn't matter. You only need one to really say you can get this throughput to the other side from A to B. The software programmers PRACE1 client.pl, which uses PRACE1 client conf, iCurve3 and FPIN. So at the end, that is a Perl program which just does this robot stuff at the end. It starts doing the iCurve for all partners and providing log information which is displayed within this web page. It creates information about throughput tests, round robin times, and HPC login nodes. iCurve3 is a client-server program developed by NRDAST, a modern automatic for measuring maximum TCP and UDP, bandwidth performance, it allows the tuning of various parameters and UDP characteristics. It reports bandwidth, delay, jitter, data graph loss, and you can get it here. The new version. Everything is similar to the big program. It needs secure neighborhood, which uses ICMP at the end. What FPIN does, it sends packets to several IP addresses parallel. So if you would use a ping, you would really send a ping, let's say 3 ping requests, it takes 3 seconds, then it takes the next side, and so on. It has to wait until the answer comes back into run, and that ping does just sending 20, 50 or whatever packets to those kind of destinations, and gets back different time intervals the answers, and just say, okay,
Do you check what's entering the voting time and monitoring the services? Is it applicable? Otherwise, it'll take a long time to time out for each place.
the amping, it really takes,
I know, but you use the app for the entering decide whether you are going to sample the site because your poster might have long timelines.
what we do, the amping is done every 5 minutes. It's still this amping matrix that I told you before, and additionally, this IPA is done once a day. In the morning, the less traffic is from users is done. So it's done in this. You have two kinds of amping. The amping I told you before with this matrix was from my network server just to see if every system is available, and the other amping which is used within this Dynamon client program is really everyone to everyone. That's also this is done by people also. It's done in someone in the morning, and that's what I said is scheduled.
But the way thing is also set here as you said, just you mentioned secure views, you might have a security problem with that.
No,
the thing is also secure views, and has to be what
the normal thing you don't do.
normal things.
You don't have to make it secure. You can give it only the permissions to bucket.
I think the normal thing is not secure.
Sorry.
That doesn't matter. It's not a security problem because it's really only I think it's secure DB because you don't want that a normal user sends thousands of packets out to the internet. It's not because of security reasons. It just sends out a packet and gets back the answer. That's multi-times. So in the amping, you get that source watch. So at the end, all this information which is collected by this PRACE client program is sent to a monitoring server at the PRACE center at Unix. The aggregated information is archived and accessible via this page I showed you before. Configuration file contains the IP addresses of systems to be tested. The passes where software components can be found. Of course, you need to know in different kinds of systems where the amping is located, and so that has to be configured. So the other configuration options, you can really say I need different options to different systems. I told you that depending on the system, you have to change parameters to get optimized values. You have to play a little bit with these options to get really the best out. And the IPM is also monitoring server, of course, because it has to send the information to this. The PRACE client conf must be adapted to local environment. To get optimal performance, hyper function must be adjusted. So now coming to the optimization of the network throughput, and here you see the preferred PRACE network options. And that's unfortunately I cannot give a list of options to set. I only can give a list of options where to look, because I said it depends on operating system, and it depends also on the version of the operating system. Maybe you have found an optimized scenario for all the other partners, and then you upgrade to the new version of your operating system, and nothing fits anymore.
Switch used to run an NDT server, which gave recommendations. The next update is still they stopped giving it service for some reason.
Yes, the main problem is it's a lot of work to do, because really it's operating dependent, it's dependent on your network card, it's a lot of parameters.
Yes, but basic things. We give you a throughput and give you recommendations, point out the bottlenecks.
So the recommendation I can give is look into these options. It's the IPQ maximum, the RFC, the 1323 RFC, the 2440, which is related to how TCP should be set up, secure selective acknowledgements, the socket buffer maximum, the TCP ECL, I don't know what it stands for.
Early congestion.
And TCP message default, TCP new label, that you use newer TCP stack, TCP no delay acknowledgement, TCP and UDP pass and discovery should be used, and TCP UDP sender and seed space should be set accordingly.
One term people often don't realize the thing to you, because if it's set an error rate, then the maximum TCP rate is linear compared to the MTU. Even if all the TCP settings are okay.
So it's a huge area where you really can look into and optimizing one parameter can lead to the fact that another one gets worse. So why are those important? Especially when it's delayed progress, this is one of the reasons. It determines the amount of data that can be in transit in the network, progress available bandwidth and the latency. Here's an example. For example, if you want to communicate from Frankfurt to, I think it was the US, it's 6,211 kilometers. And if you know a signal within a wavelength needs can transit 200 kilometers within 1 millisecond. It's easy to compute. If you have a 10 gigabit connection and round trip time, so 2 times the 6,000 kilometers divided by 200 kilometers per millisecond gives you 1.2.5 megabyte per millisecond. It's just this computed and multiplied with 62 milliseconds. So it's 79 megabyte buffer per packet you send. Per connection you set up. So the problem we see here is if you have a supercomputer with thousands of users doing connections, you cannot provide 1,000 times 80 megabyte buffer. And you don't need it because 1,000 people don't all communicate to the US. They all communicate just to their partner. Then it's 1 meter, not 6,000 kilometers. So here you already see the problem setting up the network or optimizing the network isn't easy to do. So the next one is path-2 discovery. Don't fragment packets. If you fragment packets, or if you send a big packet, it has to be fragmented. At the end, there will be several packets which have to put together again. This is work to be done, and that also leads to degraded bandwidth. And of course, using jumbo frames makes packets as large as possible. Normally, Ethernet has about 1,500 byte per packet, and if you use jumbo frames, it's 9,000, so it's 6 times. So you have 6 times, not the packet header to include. Makes it possible. The disadvantage is, of course, if the jumbo frame gets destroyed, you have to send 9,000 bytes again. So that's
if there's a high error rate, actually the jumbo frame will still improve performance.
okay. Now we have this trace route thing. At the end, it looks like this. Those are the systems, the production systems, and we just check if the connectivity to this site is possible. We have here the monitoring server. At the end, what we are doing, we do a trace route via this to, for example, between trace route from this to this systems, and then so just to check if the path is available. And here, for example, those 2 systems are not available because they are currently in production stop. And here you see it's no IP defined. I don't know that the keyword local or IP addresses because of the transition. I have to check this. Later on, NC should be green. Those are the partners which are currently the old infrastructure. CEA already got in the top. So hopefully this will be zero next week. And of course, we also have partners which are not connected, not using the PRACE infrastructure, but they can also be reached via the normal IP network. And underneath on the page, you see the trace route information. I do ping -R, doing including all the hosts which are traversed when you send the ping to the end host, and do the trace route, and you see which hosts are traversed. So just to see if it's the right connection. So monitoring and KPIs, network monitoring has been ported to the new infrastructure. Currently all net info on spatial web server, but XML files could be provided for sample monitoring, so that you don't need to go to the server, you just go to the sample monitoring server in Kenya and get all the information. We haven't done this yet. We have an offering by Geont to provide a Geont PRACE VPN monitoring solution based on personnel, and here we have again to check maybe possible to set up personnel nodes at all partners, and it also depends on how much this offering will cost for PRACE. So discussions have not yet started with PRACE operations. The pros, of course, we have less work to do. We don't have to set up the servers. It's done by Geont. And the disadvantage, of course, it's external equipment within the PRACE infrastructure. It is additional cost and coordination and integration overhead. We will also have. We have to see. It's not decided. So now I end with networking. I want to give a little bit overview about the PRACE security model. PRACE is structured into several tasks. And you see here, we started in 2004 with first thought about PRACE, and we had the PRACE preparatory phase, and since 2010 we have this PRACE implementation projects, starting with 1 IP. We are now just started 5 IP. The PRACE is structured into several tasks, and the operation is done in work package 6, services for the HPC ecosystem is included here, operation and coordination of the comprehensive common PRACE operation service, including the PRACE networking and security. And we will have links with other infrastructures and COEs also in this work package. And especially we have connections to the Human Brain Project, to ULAT, to SCI, which is Security Incorporated Environments, which now is WISE. It's a WISE community. It's a lot of security persons which think that within cooperative environments you have to think about additional security issues. For example, years ago, organization has a security policy, and you want to cooperate with others. For example, in PRACE, we have to trust each other. So what we need to know, let's say Jülich needs to know that Cyprus Institute is also doing good security. They have a security policy, they look into things, they have a security operational team, and so all those things. And of course, you may not will to provide so much information. You don't want to exactly say how your firewall rules are set up. But maybe it isn't enough for Jülich that we know that Cyprus has a firewall and that some other has looked into it and has said, yes, it's okay what they configured. An independent premium or whatever. So there are different kinds of cooperation you can do, and depending on the cooperation, you need different kinds of security levels you have to know about the others.
I think this is a good time for the security question.
Yes.
It has to be difficult. I'm the user who was the Doctors PRACE from and I started the security officer, okay. And once it got networks, all networks ended up in secure safety. And they said support someone Europe will reliably do that a lot. They wouldn't authorize connection. And Israel is a member of PRACE.
Yes.
And actually went up to the chair of PRACE, and he gave instructions to allow it, and they still got denied again afterwards. First we thought it was okay, and it was very, I think it's unprofessional. No, but someone who knows the PRACE security model, there isn't a technical reason to do it.
Maybe I really cannot. I'm not involved in this, but of course there are several sites have rules who is allowed to use a supercomputers. There is a special list of, I don't know how it's called, but special countries are not allowed to work on the supercomputers, for example, or persons from special countries. So I don't know. I don't know if all PRACE members have the same list.
Definitely not. I think it's a nation. It's defined on a national level. So if there is some, let's say, official European Union list, then I think you are not even obliged to really comply with it. So usually the countries try to comply with it, but they might have their own stricter rules allowed.
So for example, I could assume that someone asks for CPU cycles at a special system, for example, and this team looking into the research goodness of
the president was approved by the scientific community.
Yes. Those don't look into nationalities. They only look into research. And maybe they say, okay, that's fine. That's absolutely fits into the UDI supercomputer. And then afterwards, the UDI people say, but this person is not allowed because of our rules. That could be. I don't know.
Yeah.
As I said, I'm not involved.
And actually, there might be third level, which is the vendor, because in the past, like
In our case, it was a vendor.
Okay.
yeah, I had a problem that well, we had a student, some PhD student at our university, and he wanted to access our volleyball in the 2003 or something like that. So it's a long history, right? No, it's not that good, but there was a student coming from Iraq, and he was studying at our university. It was perfectly fine. But when he wanted to access our at that time IBM SGI machines from the US. So we had in the contract that we had to follow the current export policy of the US and allowance. So I really had to check the web page of, I don't know which department of whatever in the US, better knowledge of this. And I really found out that at that time Iraq was prohibited. So I said, I'm sorry, but I cannot create an account and let you access the system. And that was because of the contract we had with the vendor. Yes. That's completely independent from the national security policy.
It's the test of Canadian citizenship, which is also things that.
We also have imposed restrictions. We have to follow the US export restrictions because of the system was provided by IBM. It doesn't include this, of course. But we did have to define user, not only on where it came from, but also the nature of the restriction. It was going to be on.
So at the end, to get back to IT security, this person gets an account on the UDI system, for example. The security, IT security is okay. That's maybe a political one if he gets an account, if he gets access to the system. But that's not IT security, that's a political decision. It's maybe not good for PRACE if such things happen. You could check this in advance when you say you get CPU cycle, but that's the manager. So, a problem for the management. Let's say it this way.
No, I didn't imply you should fix the problem. I was just trying to understand. I was just trying to understand since you're on the question, why it happened.
At the end, coming back to security policy, of course, if, let's say Cyprus would say, we allow everyone to access our systems without any password. That would be a security problem. That would distract the net of trust. And then we could say, okay, we accept this, that any partner has to accept this, or we could say, no, that's not possible, Cyprus cannot be part of PRACE. That could be a decision that the management board.
Were you trying to connect to the PRACE network or to public internet?
Not public internet.
Doesn't matter whether it's Eminem or the Gian. Through Gian or the PRACE network.
Through Gian, it's not the price at the time. The person who wanted people to run jobs. And it wasn't you need to improve something, was we then authorize it. And if you guys were really talk inside Europe, it's okay.
No, there are people who block entire countries. I mean, if I'm getting a connection from, I don't want to say areas, right? I don't expect any users from there, so I block the whole country because, you know, my nodes are flooded. I'm not talking about specifically one, but this happens. You see, don't get connections from Russia, you know, because I'm not getting users. I go Russia. Yeah.
Anyway, it doesn't tell the type of membership in PRACE. It's not only, there are different types of membership and you're allowed to do different things or consume some amount of CPU cycles or whatever, it depends on the membership. So I don't know what this is the case. It's also can be an issue that you can be rejected because you are not on the at least the minimum membership you have.
Because Hank escalated to the chairman of PRACE, and the chairman of PRACE said it was okay. So I don't think that can be used as an excuse.
It's not an IT security problem. It's
Okay,
management problem. So okay, links to RFE. Before I say you were talking about SCI-wise, the ARC project, EGI, EU, PRIMA, and of course GEON. So GEON is it's the company providing the network, and it's also in the new project. So why are network and security correlated? A dedicated network allows to define different security policies to be used that public networks would allow. No interfering with traffic, no spying for hackers. So what we need is this net of trust. Here comes in the work which is done in the WISE community. So we have a PRACE security framework. It defines its security-related policy and procedures to build a trust model that allows interoperation of distributed PRACE services. The risk review of new services or service upgrades to define and maintain an agreed list of software protocols that are considered robust and secure enough to fulfill the minimum security requirements. For example, if we would like to set up a new service, we check if this is secure enough to be used in the PRACE environment. And this kind of problem started the idea of security within in PRACE already in DISA, project before, where someone said, oh, we want to set up this kind of software. The problem is on our system only, and I said it cannot be. You are connected to each other, and if you are using this kind of insecure software, you cannot be part of the data network. And we are our own musician and so on. And we said we have to set up this pro where we really discuss those things, where we decide is it secure or not, and then depending on that, the management board has to do a decision. So the management of operational security, of course, also part of the security group to coordinate incident handling with CSI team. So and that's the organizational structure. Any site has its own security team. It sends in IT security representative to the forum. We have a security forum coordinator, which talks to the management board, and the same is within the operational environment. Of course, every supercomputer has its own operational team with members of the team which sit here together. We have an operations leader, that's the leader at the end of the work package 6. He also talks to the management board, and of course here operational policies have to be exchanged. Is it allowed to use the service? We have a new service, we can check it and so on. So all partners provide members to the PRACE CaSToRC team. Site incidents must be reported in case of possible impacts on sites. Of course, that's a problem. It's really local and doesn't have any impact. Doesn't need to be announced to the others, but if it's something which could others affect it should. Vulnerability reports have to be provided, no formal documents, any available sources for information can be used, stored in the PRACE wiki, sharing of emergency phone numbers and security mailing lists for all sites, and we know who to contact if there is a security incident. Although every partner is expected to have already informed information about vulnerabilities in general, it is helpful if specific information is also provided through internal channels. For example, if you get information that there is a problem with some software components, you could send it to the firm to inform all the others, maybe they have not this information. Especially if you know that others have the same software components implemented. Let's say GPFF or
Depends if you get the latest from the policy. Sometimes it depends. A lot of security vulnerabilities are given, and you're not allowed to redistribute it.
Yes, it depends. I'll come to this later. So security policies and procedures, minimal security requirements that all PRACE sites are expected to abide to, agreed list of software protocols that are considered robust and secure enough to provide these services, trust model that allows smooth interoperability distributed PRACE services, policies and procedures address the risk review of changes in the infrastructure, the handling of security incidents, the auditing of security setup, the roles and responsibilities of personal teams. We also have risk reviews, the security firm performs a risk assessment of new services or updates on existing services. If changes in security setup come up, prerequisites here are provision of security policy documents by every site, and possible self-assessment using a document published by the SCI group and the advice group. That's again here, of course, not everyone wants to provide all the information, but we need a special level of information that you have something that you secure your system in a way that you have good passwords or keys or whatever. So this is information we need. So collaboration and security with other projects and activities mostly handled in work package 6.3, which is led by Stefan, who is in the other track of this meeting. We have collaborations with EGI, new brain projects, and UDA to CaSToRC by sharing information on incident and vulnerabilities. Enables exchange of information about incidents if there may be cross-domain impacts, and also exchange of vulnerability information. Several PRACE colleagues are from the EGI, UDA, and HPP security alert lists and vice versa, so we really interact there a lot and exchange all the information which is needed. So coming back to your question, we plan to be part of the Trusted User Program, which is a service from Geon. You can register your team there, or let's say there's 3 stages. You can list them, which provides basic information about the team itself, as well as shows endorsement of the team by the community. You can be accredited, which ensures a defined level of best practices and acceptance of the established TI policies for such teams. And you can be certified if they have been accredited before and prove a confirmed level of maturity as defined by the TI framework. We want to be accredited. Certified is a lot more work, and we don't think we need it. And accredited really means you get much more information about incidents, about vulnerabilities, which normally have the levels green, and so on. And here you can get much more information because they know you do good work within security and you are worth to get this information. So what really means accredited for the teams is access for listed teams is self-service interface for updating information, access to in-depth operational data of all accredited and certified teams, restricted and encrypted mailing lists as well as restricted but not encrypted mailing lists for administrative purposes and open discussions, attending events like meetings and trainings. Members can attend the open TFC meetings and closed TI meetings. Secure out-of-band alerting system, restricted and protected alerting services using state-of-the-art mobile communication, as well as traditional telephone communications are operated to provide crisis communication independent of the internet. And what you can additionally secure IRC server, restricted and protected IRC-based discussions to enable real-time collaboration on learning issues, public key infrastructure, member teams representatives, as well as individual team members getting extra online certificates in order to get access to restricted and protected services and interfaces. That's what I just talked about. You can download CSV files with contact information about all teams registered by the TI, including accredited and certified teams. In addition to GPG, PGP key links are maintained and made available, and the TI compendium, quick orientation of teams and such useful reviews to the selected teams. So that's about the accreditation. And one more slide about the PRA, it's the European Policy Management Authority for Grid Authentication. PRACE trusts CAs accredited by human PMA, or the other two PMA federated in the IGTF and the Interoperable Global Trust Federation. PRACE is also a relying party of the human PMA, and those teams meet 3 times a year at a face-to-face meeting, and this is attended regularly by PRACE representatives. And last but not least, general principles. Each PRACE site is responsible for the management of its own users. User registration or certification methods may slightly differ from site to site. The PRACE accepted use policy applies to all users of PRACE. Some sites may have also specific regulations related to security, and this is exactly what you just mentioned. So there's a general concept, but there may be special regulations on the system. The PRACE security model has been in production for now more than 10 years and proven to fully fulfill the security objectives related to the PRACE needs. PRACE is following closely the identity federation initiatives, and interoperability with other project communities and industry is the main goal. I must say the security model was good for the last 10 years, but maybe there was no real attack. That's always with security and insurances. That's it. Yes. Any questions? Coffee break. If there are no questions, thank you for listening. I assume that you always
we get the
Sure. חושב שהוא סיים את זה?
לא, אני באמת, אני מרגיש כאילו... אין לי שום מושג בכלל מה הוא רוצה. מה הייתה הפואנטה של ההרצאה?
שום עצמי,
שעתיים וחצי. שיסביר מה הוא עושה אז. אני לא יודע, אני הגעתי לכאן בלי לדעת מה הוא עושה. מה הקשר שלנו לזה? איך אני משתמש במידע הזה שהוא נתן לי?
מי אמר שהמטרה זה...
אז אני חושב שלא עונה לי.
בוא.
מה אני עושה במידע הזה שנתן לי?
לא, הנה, שם כאילו שם.
אנחנו מחכים את זה משהו, זה חלק מהחברות של פרייס, זה לא ששאלת, שאנחנו יכולים לפרייס, כאילו לא שזה פרויקט הבא, לא בא לי זה נתון זה משהו, אתה יכול להתעסק,
אבל לא,
אבל
אני יכול להשתמש בישראל אין לנו ולכן זה חייב אין לנו כי זה נושא יש לנו לא, יש לא, אבל
אם מישהו שתהיה חשוב, הוא צריך להגיש הצעה,
אין להם אוקיי, ג'יאן זה הרשת שמקבלת את כל האלמנטס באזור ג'יאן זה האפלינק של אוקיי, פרייס זה לא זה
הסיפור של הציבור. אז יש שם סרטים.
Yes. Okay, I just sent you an email with your contact details. So you have was
Yeah, I cannot reach as a J or G. Just right in the back. Yesterday. Yesterday.
Managing others.
Now that we are announcing the final one, the 195.113.250.16. The one where I show you the one. I will just check with you more. First thing, your upper fundamental function is the rest of the So there might be some going through it.
This one second. I can actually test the space with the multiple. So I have to contact my girls and meet and she rerouted back to the VPN.
Yeah, actually what I can do, I can trace route and see how it's yeah, but it definitely doesn't go through our power. So I use CSC as the Swiss Python thing. Yeah, because I can access CSC and I can access Chinook, but I cannot access your okay. So if I try anything else, then Chinook, it should be okay, right? No, I mean, okay, so everything is a general not sorry. So I would say actually, because I can pay now CSCS and I can pay Chinook elements. Let's try to see CSCS. Oh, yeah, that's good. Yeah. But I think we can think that yeah, that might be, yeah. Okay. Yeah, but I think it's part of this, so I can think otherwise, oh, yeah, yeah. Yeah, yeah. So I can probably launch yeah. What's the one that just has all these sites, but just some reasonable ones? I hope so. That's why I'm doing this. My point is that when I look at the tests, I have some real numbers, and I think it's mostly so right now I don't know I hope that's not my experience. Yeah, of course, yeah, that's say some money also. Money is just fine. Something we can get. Don't forget that.
Yalla. Okay. I will.
All right, I don't see our host, but I guess we'll go ahead and start since it's after time to start.
You introduce yourself.
Yeah, I guess I'll introduce myself, so. So hopefully everybody else is set up, so my name is Brett Bode, I work for NCSA at the University of Illinois in the US. I'm going to talk about system monitoring and in particular talk about what we do for system monitoring on the Blue Water system, which is one of the largest systems in the world still today. So why is system monitoring important? I guess that's not too hard to figure out. We first of all want to make sure that science jobs actually execute correctly, that users don't complain about them. Ideally, we also want to know about a problem before the user reports it in a ticket. That's always useful. It's always useful to tell the user you've already fixed it when they send that ticket in, actually, when they say their job failed. But certainly enabling quick diagnosis of problems is a key piece of it. We also would like to collect system usage information so that we can learn about how users are using the system, both to hopefully help them use the system better, as well as educate ourselves on what we should do differently on the system, either in managing the system or to identify opportunities for improvement for future systems. So there's quite a few different ways to do monitoring. There's usage tracking, which is pretty straightforward. You usually do that via the batch system sort of thing. What are people running, how are they running, that sort of thing, kind of keeping the system busy. You can analyze utilization of system use resources by applications. That you can get some of that from batch system information, but some of it has to come from other mechanisms, and that gets a little more tricky to pull out. Some of that can be Alt-D or Excel sort of information. Some of it can be metrics that need to be collected from the nodes. There's also monitoring that you do proactively. So how do you know the system's running well? Just because you have an alert doesn't mean it's actually running well. So you need to actually run routine diagnostics to be able to say that the system's running as you think it is. So active functionality and performance verification. Of course, we talked a little bit earlier about system log collection. There's a whole lot that goes into collecting those up from a large system and analyzing them, generating alerts appropriately from them. It's very easy to get the illusion of overwhelming volume of system logs. Sorting the little nugget of information out of the volume that's coming out of the system can be quite challenging. And finally, of course, we'd love to be able to collect
performance metrics off of every compute node of the system, so we can actually tell what's going on in a user application. Is it behaving like what we expect it to behave? Is it one node slower than another, or something like that? So there's lots of information we can glean from that information. But collecting performance metrics is not without its problems, particularly in terms of the deluge of information. So I started here a little bit with a plot that we actually have on a user portal. This happens to be one from a couple of days ago, and it was a very large job running. I'm actually going to switch out of this, I think. Does this work? This was actually just a little while ago, same sort of thing. So we plot we have a PRACE Gemini interconnect, which is a 3D torus. If you're not familiar with the 3D torus, just think of like the 3D cube, which is also displayed, but the edges are wrapped. So there is no edge per se. So if you see something on one edge, it's equidistant, or its nearest neighbor is both the thing next to it and the other edge. So you don't have to worry about the edges. But you do worry about when things are far apart, because that means you have many hops to connect to get from one component of an application to another. So one of the things that I want to talk about a little bit is an effort we did to do polygon scheduling on this torus. And that's why we get these nice compact shapes. You notice all of these are cuboids, basically. That's a feature of what we're doing there. It does lower overall utilization, but we've been able to show it actually improves science throughput. And that was through a lot of data collection and analysis in order to show that. So this is what happened to be running now, which is a fairly good sized job, about 10,000 jobs, plus a few smaller jobs. And in case you're wondering why we would prefer planes like that versus something more cubic, it happens to be some artifacts of how the PRACE 3D torus works. There's 3D torus is bad enough, but you've also got to worry that the three different directions don't have the same bandwidth and characteristics. So we actually prefer planes rather than cuboid shapes in general. All right, so back. I'm going to try to be a little dangerously to actually do and actually do live demos when I can. So just to review what Blue Waters is, I'm not going to talk a lot about it, but Blue Waters is the National Science Foundation's Track 1 system in the U.S., which is the largest system that the National Science Foundation supports. It's roughly similar scale to other leadership class machines in the U.S. It was deployed and operational in 2013, so we're actually 4 years into operations today. So that makes it a little past its prime. However, it still has some metrics that are still pretty impressive. It's about 13 petaflop peak system, still top 10 more or less in the world. It's got more memory than we know of on any other system in the world, so 1.6 petabytes of RAM. We have a few other things like a 26 petabyte usable file system, which is not huge by systems that are going into today, but it still keeps up pretty well with the fastest file systems out there. So we have a 1 terabyte per second sustained user accessible peak I/O rate. We also have 200 petabytes of tape storage as a second tier of storage, along with we just upgraded to 4 100 gigabit links out of our data center to support wide area transfers to national and international networks. Overall, this is kind of more of a numerical view of it. We have about 26,600 or so compute nodes, a little over 27,000 total nodes in the system. About 4,228 of those are GPU accelerated nodes, where they sacrifice half the cores and half the memory on the node for a NVIDIA K20X GPU. The rest of them are dual socket interlagos compute nodes. The main thing I want to get out of this, when we're looking at this from a monitoring perspective, is we have a very large number of compute nodes. That's not too surprising. We also have a lot of service nodes within this fabric. Those boot off of what Craig terms are system management workstation. So the logs on this stuff flow through the SMW. The logs on our file system flow through a separate fabric over here. We have about 100 nodes that are data movers or login nodes or other management nodes that flow through a separate external server infrastructure, plus switches and that sort of thing. So we have a number of different networks and administration points that we all have to gain logs through and flow through in order collect them in a single location and analyze them together. So one of the things to point out here, and this is not meant to be something you're going to read, but this is a network diagram for blue waters. And each different color is a different logical network. So there's a lot of different administration domains within this. And you have to, our main log server had to have some way to get logs. Actually, our main log server is right here. Has to have ways to get logs from each of the different administrative points in the system. But we also wanted that log server to be something internal where we could actually do things on it that we didn't want general user accessibility for. So we have to be very careful that this doesn't become a security problem rather than a benefit. So we have to take some significant efforts to make this span our network. Today, we collect about 8 billion data points per day off of blue waters, which probably is one of the most monitored individual systems out there. That spans from various logs to a lot of it comes from performance metrics. We actually collect about 100 different metrics once per minute from every compute node in the system, which amounts to quite a bit of data flowing through a system. So that's not just a big data flow problem, it's a big data storage problem. So we're unable to store them for more than about a day or two at a time, or a day or two's worth at a time. So we store them long term on spinning disks, but we can't store them in our high-speed flash that we can actually do a lot of our primary metric analysis on for longer than that. So, but we also collect things on our file system. We collect a lot from our work and our Moab scheduler, from our IB switches, the HPSS cores, information off of our external logs, tape system, and lots of other different sources. So that all flows together in one system that allows us to do some analysis on it. That's still not easy. There's a lot of data collecting the data is a lot easier than doing analysis. So we've got several different ways that we do that analysis. Some projects we've done have panned out better than others. One that we use is XDMod. How many here have heard of XDMod? Okay, so it's an open source project that came out of the Exceed program in the U.S. It's a system that ingests various batch system data, basically. We use it with Moab, but I believe they support other Slurm and other different schedulers as well. The reason that it's interesting is that you can ingest quite a bit of data, so you can keep track of a lot of different metrics for clusters and grids. Users can access it and see similar sorts of things. Didn't actually know this was had animations on, but and it lets administrators to look at different things as well. I'm going to show that in a second here. Let's see. So this is where I'm just going to switch over here. So there's various different charts that you can show here. It happens to be kind of a front end chart that just showed kind of average job size, total CPUs, CPU hours by job size, different jobs by PI, and that kind of thing, which are somewhat interesting at different times. We use it more for a different purpose. I'm going to jump out again. Find the right window. All right, so one of the things we do on a weekly basis, if not more frequently, is analyze how we're doing in the system. So we look at things like utilization. Don't worry too much about the right 2 points because it's pulling torque data, it only knows about jobs after the end. And since our maximum runtime is 48 hours, there's usage here that's not actually known about by torque yet or by the XDMod yet. But what we use this for is we can go in and analyze things such as we want to know things like wait hours, so how long our jobs are waiting by queue, so we can dive in and look per queue. And if we want to then dive in and say, okay, why is this spiked up so much? We can keep diving into this sort of data and look at who is doing what on the system and what's driving the different metrics. So wait hours leads to expansion factor. We want to know why somebody is blocked in the queue, because they're probably the ones that are going to be yelling about jobs stuck in the queue kind of thing before too long. So that's the sort of thing we'll look at fairly frequently. We can look in here and find out who's doing what, that sort of thing in here. So this is one tool that we use fairly frequently. This is actually open. I'm not even logged in. So, this happens to be XDMod at NCSA. If you use XDMod in general, the Buffalo site, you'll actually see all of the seed machines. So you do multiple sites, multiple machines as well. That's what they actually wrote it for. We're using it just for the waters in our particular instance here. But we use same sort of thing here. To analyze this sort of data, users can drop in and do the same sort of thing. This is all user accessible. It's just all analysis of torque data, so it's fairly straightforward, but it's, they do a nice job of providing lots of different ways to slice and dice the data so you can find different things. It does not, this particular instance does not include performance metrics. This again. We did, however, work with the University of Buffalo to extend it. Of course, I'm not sure this is available in the open source version yet, but we added ways to ingest all of the data that we have for Excel Darshan, which is an IO performance analysis tool, and our OBIS metric collection data, pull all that in, and about, for the first 3.5 years of Blue Water's production, several terabytes of data that was pulled into the database and summarized. This is actually a link to the full PDF version. I'm going to give a bit about from that. But it's a workload analysis of Blue Waters, and it lets us take a look at characteristics of user applications of the system. How are users using it? What are the most popular applications? How did they use the system? And with this addition to it, which hopefully will become public soon, you can look at a lot more different types of things, like how was the CPU, GPU utilization per user or per job, or that sort of thing, or even network and IO utilization for science teams. So some insights that we gained from that, and just in terms of top applications on Blue Waters. The top one, which for those that know much about US, NSF, but the top application for us is actually NAMBI. That's not too surprising. NAMBI is one of our largest applications and used by multiple different teams of development at the University of Illinois. We have a number of others here, Milk and Chrome being top ones as well. So this is not too surprising. This is the first 3.5 years of total node hours, so NAMBI almost got 100 million node hours in that time period. We also can break it down by whether they were using the GPUs or not. So red is teams that were using GPUs heavily. The number of the bigger teams are, but we'll note that there's not that many GPU applications here. So this is one of those things that we're looking at for future systems. Are users and teams making the jump over to using accelerators effectively? It's not too surprising that the molecular dynamics folks are really the heavy users of it. I think everybody has figured out that MD runs really well on GPUs. They get something like a factor of 8 speed up on a K20X versus what we had there. So they really like the P100. So Amber in particular tends to be more of a single node GPU application. They just run lots and lots of different runs. And NAMBI tends to be more parallel, but both of them can make very good use of GPUs. So those aren't surprising. We would like to see more other applications make use of them. We talked a little bit about yesterday about library usage data, and this is kind of how we pulled some of that out. Once the Excel data was parsed, look at what libraries are in use and what versions and that sort of thing in there. We also did GPU analysis, our analysis of GPU usage by application. I looked at actual utilization, and some of them is not too surprising. Amber is better than NAMBI. Amber's a single node, single GPU tool. They're going to get better utilization than NAMBI that has to scale out for large runs in general. But others are all over the board. So we look at this particular plots application versus node hours used versus GPU percent. So this shows different sorts of things that we can get out of it. This is a plot I happen to like actually quite a bit. It looks at job. Each one of these dots is a job size. The color, as it gets higher up, the color scale here indicates more jobs of that size on there. The node counts across the x-axis, and peak memory usage is on the y-axis. So as you move up the plot here, we can see how frequently jobs are using all of the memory on our nodes. So our nodes have 64 gigabytes of memory. So one of the questions you can ask is, somewhat anyway, what would happen if we were to have the memory size of our system in a future system, and that'd be kind of a diagonal line across here. Some of the work above it would be disadvantaged. Some of it probably could adapt, just scale it along nodes or something like that. But some of it needs this amount of memory and therefore wouldn't be able to run. So that's where we start to look at it. It's always nice to see something like this. So a lot of these jobs are probably test jobs because they're running at like full 26,000 scale of machine. These jobs tend to be roughly the full CPU node usage of machines, for roughly 22,000 node sort of job sizes, and there's a few more of them, but a number of users that use that sort of thing. Happens to be, this is sort of an interesting point because if you map it across to memory usage, you can see that those jobs are actually using more than a petabyte of memory for each of those jobs. So one of those interesting data points that we like to show the reason that we paid for all that memory. So.
Are the nodes same?
The 22,600 are all CPU nodes, all have basically the same amount of memory. We have upgraded a small number of both types of memory, like 96 nodes of each, to have double that memory, so 128 gigs per node. Of course, that's all PRACE supported in that generation of architecture. So it gives a few people a little bit more memory for mesh generation or data analysis sort of things, but it's not enough to make a big difference in the total size.
So if you have to make a choice now, how much RAM would you put on the
Well, we're having to make that choice going forward, so that's one of those things we're still arguing with it. One of those things actually we're going to some of these science teams that are running this sort of code, start to talk to them about that. Because if you look at future generation systems, particularly those that are in that 2019, 2020 sort of time frame, you start to have a choice between, do you go with a system that has traditional DDR memory, in which case you probably have quite a bit per node, the per node may not be as the core count's going up, it may not be as much before. Or do you go with a system that has HBM memory? Because HBM memory in that time frame is very limited in size. And so the memory per core in an HBM sort of architecture is quite a bit more limited. But it's quite a bit higher bandwidth, so there's a trade-off there. So we are trying to answer that question as to whether that would make sense or whether we need to stick with a traditional DDR solution and more volume. So look at functional testing. So this hasn't been, we targeted doing this early on in Blue Waters, but really only got our acts together and got it together in the last year or so. We had lots of tests that we put together at the time of acceptance. Some of those were short functional tests. Some of those were multiple hour sorts of things at full scale to prove that this scale system. You can't run full scale system jobs all that often. That's not practical. You usually only do that sort of thing after a major upgrade or change of the software when you want to revet the system. But we do have a number of small scale tests that we can run frequently. Some to vet the system and some that we also use to just check from a user point of view how the system's behaving. To do that, we started about a year ago to use the Jenkins continuous integration system. How many people know about Jenkins? Probably it's similar to Travis CI, if you haven't seen that sort of thing. So these are our standard software development continuous integration frameworks, so nothing particularly new about them. I'm going to switch again. This happens to be our Jenkins interface. Switch over to So this happens to be our Jenkins interface right now. I've actually sorted this by last success. So some of these tests we run quite frequently, and some of them are actually more about vetting the system than anything else. So let's look at this one. So this happens to be a very simple test. It actually we basically run this test frequently on the system, like hopefully once an hour or so. I think that's what the idea is. Actually, yeah, that's all like 1.6 is all day. And it's looking at the time it takes to do an LS on our scratch file system. Nothing earth-shattering, but if you're familiar with Fluster, when metadata performance goes in the toilet, LS takes forever. So this is sort of looking at what users see when they're looking at each of the file systems. Because we start getting tickets. LS is hanging, or whatever on VI is hanging because I can't exit out of my shell because or something like that because their file system is is slow. So this is some measure of what users are seeing when they're actually using the system. So this is not particularly proactive in that we're not generating alerts from it, but it lets us go back and look over time. When we got that user ticket in, what did our tests say? Oh, well, we had this spike, and this is not terrible. I think this is in seconds, so this is 6.5 seconds. So those are 6.5 seconds in an LS that normally takes less than half a second. You know, users are probably going to notice it, but they're not going to complain. But it starts taking 30 seconds or a minute, then they start to complain. So, and we do see that fairly frequently. And these are really quite simple to set up. See if I want to be here. I'm not the one that sets these up normally, but basically there are tools within Jenkins to do remote SSH, and so that's basically what we're doing, and then just packing the data into the entire tool here is just running a couple scripts on the system to do this. So really quite straightforward thing to set up and run, and then plot the data out and back in. And that lets us do a little bit of this continuous sort of integration stuff. But we also run some other tests that are actually some of our small scale functional tests from our acceptance criteria that we can run periodically. Some of them we run automatically. So like this sort of test, I don't know if I've got it here as to how often it actually runs, but all right, well there's every 5 minutes basically, right? So so this one runs very frequently. Other tests we don't run automatically. We have them set up so that after a software upgrade we can punch a button and it runs a whole suite of tests to vet those sort of things. So
I'm just curious how Jenkins compares to Nagios in this instance.
So I haven't used Nagios to do this sort of thing. I've seen Nagios used to do more general monitoring sorts of things, but I haven't tried to do this is actually, in some ways, this is an interesting test because this is an external system. So it actually has to log into the system to run this test. So it is actually getting some you're seeing user behavior from this. You're logging into a login node. Some of these actually do a QStat or something like that, interact with the system. You can probably do some of that with Nagios as well. Like I said, you can do this with Travis CI or other continuous integration. You can probably do it with Nagios as well. You just have to figure out how to pop the data into a formatted plot, kind of thing. So whatever tool works for you, I guess, is certainly useful. All right. This was just setting up the test again. Some of the other tests we run periodically, similar to the LS test. This is a small metadata MD test run, and this was a couple days ago for a few days. But you can see it varies substantially over time. These are all probably reasonable, but we do kind of keep an eye on things when they start deviating substantially. Do we have a problem we need to go look at? Because I'm not sure about you, but our file system generates more user complaints than anything else. So this is something we get to look at multiple times a week to see what's wrong. So we do that. We do a small ILR. And this one's great because this is all pretty solid. Everything's looking quite solid here. There are many times it doesn't look anywhere near that good. We also have, this is a small NAMD run. Obviously not very long, it's only 240 seconds sort of run. We're looking at over time. Again, this one's pretty good because the variance in here is only a couple seconds. So they didn't have any major outliers, and that's a good thing. So that's the kind of thing we would like to see. We don't always see that sort of thing, that sort of behavior. All right, so moving on.
So the full suite of tests you're using for this, is this something that's publicly available, or
it's not publicly available today. I don't think we'd have any problem sharing it. It's just one of those things that we haven't had time to actually package up. So if you want to shoot me an email, I'm sure we can talk about sharing it. It's a work in progress. Like I said, we originally planned on using a different tool that didn't pan out very well for us, so I'm not doing that. The driving tests. So about a year ago, we started using Jenkins, and we started migrating tests in, but we haven't got everything in like. All right, system logs. So I mentioned we're doing a lot of log collection. Blue Water is basically everything's forwarded to one upstream collector. That's either done through our syslog or LLM, lightweight log manager, which is what Cray uses on the Cray parts of the system. We originally developed a custom analysis engine that was going to do automatic generation of templates and that sort of thing. That sort of worked, but not well enough that we're still continuing to use it. So at the moment, we have fallen back, and the primary analysis engine is we're using right now is SEC, which is simple event correlator. It's a very simple sort of regular expression matching sort of thing that looks at log streams. I'm going to talk about that in a minute. Certainly, if you were starting over today, which we're not, we just had SEC for 4 years now. But if we were using the ELK stack, would look pretty attractive. So I'm not saying what we're doing is necessarily what you want to do if you're starting from scratch, but it's not a bad place to start. So the SEC software is a simple event correlator. It basically you're just reading in files and pipes just entered in, and you're matching lines with patterns. So these regular expression control subroutines, and you can output via a variety of methods. We generally use email for most stuff, and then generate, well, actually email for everything, but some of that email can be generate a page. So at least in the US, we can email basically, or phone number, cell number to get a text message. For the primary NCSA staff, we generally are only doing email. Some of our PRACE staff on site also use the paging capability. So certain types of events, they page the on-call for so that they know they have to wake up and go in and replace something. So when something like something that knocks out a Gemini node in our interconnect, when that drops out, that's something that's sufficiently perturbing the system that they'll call 24/7 repair on. Other sorts of things like a general node failure that doesn't impact the network is taken care of the next day or the next week. It doesn't really matter that much. Overall, this is still too noisy to be terribly useful for alerts, for the general email alerts. So we get about 120 emails a day out of this system, and that's sort of for any of us too much to actually want to sit and sort through. So it's useful when we know there's a problem. We're going to go back and say, okay, where did that happen? It's not so useful for generating the raw alert, other than the more selective ones that they do via paging. There, so basically, it's a very simple daemon. Sorry, I said that. So we use it on servers. We use it on our network. We can actually use it on the networking equipment as well. That didn't know where I thought it was going. All right. So anyway, this is a simple example here. Again, very simple config file with a regular expression matching pattern. So it's pretty easy to set these up. I think there's a good set of examples or samples probably out on the web already. So it's not a terrible place to start. So basically, you tell the type, you tell what type of expression matching you're going to do, the pattern, the description, and what kind of action you're going to do. In the example, there's also a delay, so that you're not going to regenerate the same alert for some period of time. So some alerts have longer delays than others. What we get out of it, this happens to be an email generated out of that. In this particular case, it's a cheat check exception, so based on a memory hardware error on a particular node. This is something that our PRACE staff goes through daily, because they got to go find the nodes and why they failed and write up a case for each one. But they have lots of paperwork to do. So, but it tells them, oh, this is a memory error, so okay, I'm going to shut that node down. I'm going to have to replace it at some point. So, they'll take care of that. The NCSA staff, we don't really look at these particularly, other than if somebody writes it and says, oh, I got this error in my application output, job failed, what does this mean? We can go on and look and say, okay, well, you got a memory error on that particular node. That happens. We lose, on Blue Waters, we lose about 2 nodes per day, which is actually far below what we should be seeing. So 2 out of 27,000 is pretty darn good, actually. So, so if you invert that, our mean time to failure for a node is on the order of decades. So it's actually quite good.
You know how which component is mostly activated?
When we're looking at hardware, on the hardware side of things, it's exactly what you expect in every other system: memory and CPUs. But of course, if you look at the node board for Cray, there's not many other choices. So you have memory CPUs, the voltage regulation, and the Gemini. That's it. No local disk. No, we have our racks have one moving part in it, and it's a heck of a big blower at the bottom of each rack. Everything else is solid state. The node boards will have 4 nodes per board, 2 sockets of AMD interlagos, the DIMMs, the 64 gigs of memory. Like I said, the connections to the Gemini, 2 Gemini chips per board, and some voltage regulators. That's it on a node board. GPU nodes have GPUs that are part of that, but it's similar. So that's one reason that they're very reliable. There's no regular fan failure, that sort of thing. So that helps a lot in reliability story. But that is, still the failures are more or less what you expect. We do occasionally have something more interesting fail, like a fan in the bottom of the rack and the whole rack EPOs. That those do fail occasionally, but fortunately not too often. So that's the sort of thing we look at. And EPOs are a little more interesting to see because they'll come in similar emails. They're also generate a page to Cray staff to see what's going on. So we do have those occasionally, either from cooling component failures, fan failures. We've had power supplies. There's seven AC to DC converters that convert the 490 volt AC power into 60 volt DC or something like that. Puts up on the rails. When one of those blows, occasionally it shorts out. It has a short circuit long enough it blows a breaker to the rack, which is not supposed to do, but occasionally it does. And that causes the whole rack to go off. So then we have another issue we got to go solve. So anyway, so those are what we get out of the system logs for the most part. We get some other things out of there that help us do analysis as well, but that's an example. So I want to move on to the performance metrics side of things. So ideally, on any system, you'd love to have very high resolution metrics for any job in the past that you can go look at. Because if you have sufficiently high resolution metrics, the users can actually get insight into the performance of their application over time, similar to what they would get out of a performance tool that can be more intrusive. Collecting those metrics, however, can be a challenge. Traditionally on PRACE systems, PRACE actually made the system so lightweight they didn't do any performance metric collection at all. Said, that's going to generate too much jitter at scale, so we're not going to do any sort of metric collection. That's part of it. That's partly true. But the other problem is, of course, that as you're collecting large numbers of metrics, you got to store them somewhere. And as I mentioned, on Blue Waters, we can store them for a little while, but we can't store them for a long period of time. And we don't even collect at a very high resolution. Once a minute is good enough for most of the system reasons we want to look at the metrics, but it's not good enough for a lot of the user reasons that they might want to look at metrics. So they want to look at stalls or something like that, or load imbalance. That's harder to do when you do a minute resolution. So when we look at metric collection on smaller scale systems, something like Ganglia, I'm sure many people here are probably using Ganglia. It works pretty well. It's a tree fan out sort of thing, but it has its issues in terms of metric collection on a large scale system. So what we use instead is a project that's being developed out of Sandia National Lab in the U.S. They also have some PRACE systems, which happen to make it very amenable to our PRACE system as well. But their goal was to make the collection extremely lightweight. And the way they did that was making use of the hardware acceleration on the system. So instead of having either pushing the metrics up the tree or having a collector pull the metrics, they do something a little bit different where basically the clocks are synchronized. Somebody else mentioned clock synchronization is very important. It was very important for us too because our metric collection is based partly on having the clock synchronized. The daemon wakes up, collects the metrics on the node and sticks them into a special registered region of memory on that node, similar to what an MPI application has with a registered region of memory. So these daemons have a registered region of memory, and then a collector daemon running a service node can then independently pull that data, those metrics out of that node without interrupting the CPUs again, because they can do an RDMA over the Cray network. The Cray network hardware will take care of pulling that data out of the memory. So that lets us avoid, we have only one interrupt and not be dependent on the network collection to create jitter on the system. With that, we've been able to demonstrate on our system, which is the largest Cray system that they've got in terms of node count, that we can get down into sub-second metric collection frequency and still not have any significant jitter impact on applications. So that's great. Fortunately, we can't store that amount of data flowing off the system. It's just too high resolution. So that helps us pull the data. Then what are we going to do with it? So as I mentioned, so there's a lot to get with the clock synchronization. We get very synchronous collection. Like I said, we did it down to a second resolution without any measurable impact. And we can store that, then we can store it all in a file archive, and that works well. Much of that data was parsed and pulled into that workload analysis, and that's where we got things like network injection, things like GPU utilization. That was done by then summarizing over the time of a job for each node of the job what the utilization was on that series of office data. That's why it took a long time to parse a lot of that data, because there's a lot of things that had to be taken from raw metrics, summarized by job before it could be put into the database. This is kind of what that looks like, as I mentioned. So the compute service nodes, there's an aggregator that actually pulls the data across, sticks the full data set into Lustre and into our integrated service console for a single log machine. That sticks it here into high-speed flash memory, which we can store, roughly a terabyte or so of data, so a few days worth sort of thing. This lets us analyze it via HTTP. So we collect a lot of different metrics, ranging from what you might expect, free memory, load averages, sort of thing. GPU utilization, we pull the GPU counters off the system. We pull file system information, bytes read and write, that sort of thing. We pull Gemini, the network performance statistics as well. We pull lots of network injection sort of things in there, as well as other NIC statistics on that sort of thing. So this lets us get a lot of data on each node and look at different ways we could have bottlenecks in the system or other problems. So what do we have here? So it tells us something about the sizes here. So we're running the node data, about 35 terabytes of node data. We can pull about 30 gigs per day of node data. So there's a lot of data that's flowing in the system. We can only hold so much of it. But we support a number of different tools to extract it. And eventually we're going to publish the data sets. The workload analysis was the first derived of work coming out of this data. But we eventually want to publish the entire data set. But other things we do from our monitoring data, this happens to be one where we look at, I mentioned we keep, one of the other things we keep tabs on in addition to our file system is our scheduler. So our number 2 thorn in our side is our scheduler. How many people use Moab Torque? Not too many, actually. So, yeah, so Moab Torque, we have a love-hate relationship with them, but they run pretty well for us, but we have a lot of issues in terms of scale with Moab Torque. So let's see if I can get here. All right, well, anyway. So we have pages that are on our workload system. This happens to be a relatively live view, current utilization of the system. We also look at our backlogs and our draining time. So anything below the axis is related to draining. These have to be reservations, so show our reservation depth going forward. One of the reasons we keep track of that is to understand the backlog of the system, because if there's not a sufficient backlog in the system, the scheduler doesn't have enough to work with in order to pack stuff into nodes in the system when our utilization suffers. So we keep a pretty good tabs on this, because the users come in and complain. We say, well, look, you didn't want submitting workloads. So there's pieces of that. We actually do both XK and XE sorts of plots to keep track of that. Let's see, what else do I have next?
What version of Torque are you in?
We are, let's see, Torque is 6.02 or something like that. It's like the latest version. We have to be pretty up to date to get the topology word stuff. In fact, we often are running something that's not quite a released version because of that. So, yeah, so it's a bit of a challenge. The other thing we have a problem with TORC, and I even show a plot of that, we actually, that's such a problem we have is the schedule iteration time. Probably nobody else in the room has this issue, but we have it in spades. Because between the node count on Blue Waters and the number of jobs in the queue and number of jobs running, it could take a long time for the schedule to make a single iteration. And if you know MOA, something block on that. Certainly you can't start a job unless there's a schedule iteration time. In fact, maybe I can pull it over there. It's actually an interesting plot. One of these. Mouse first. Too many tabs open. I don't know what that one is. Oh, good. My browser's pretty on me. All right, so we'll look at that in a bit, I guess. So we actually plot schedule iteration time. Good schedule iteration times on Blue Waters are a couple minutes. Bad schedule iteration times are like above 10 minutes. So it's very impactful. And that's partly because, like I said, because the number of nodes, it's got to pull node data of 26,000 nodes every time, every iteration. It's also got to pull job data on all the running jobs. We run, depending on the day, right? I can probably tell you right now.
Why don't you put it on the supercomputer?
Yeah, let's see. But Moab actually doesn't run in parallel, does it? Yeah, so it's so we have.
What do you run? What do you run?
We have a Crate traditionally runs it on one of their service nodes on the system, which is basically CRUD node. We've externalized it, so we're running on a reasonably powerful, reasonably recent Dell server. But only certain things on Moab are even multi-threaded. So there's only so much we can get out of it. But we do, some people have suggested we just, as a defensive measure, restart Moab about once a day because it likes to hang occasionally too. In there. But let's see, current running applications on the system as downloads, but 973 was over 1,100, sometimes as many as 4,000. That starts to make it bad. For idle jobs, I guess. So total jobs in the system, lots of health stuff too, but about 4,000. So 4,000 jobs in the queue. So that means there's probably about 500 that are actually idle, but there's about 2,700 that are sitting there that are dependent jobs or blocked for some reason. So fortunately, I think Moab doesn't look so much at the block stuff, but it's got about 500 jobs to look at that it has to make some sort of decision on. We also set our reservation depth to as much as we can tolerate. By default, Moab only uses a reservation depth of 1, which means only the top job is getting a reservation. That can cause a lot of issues when you have a lot of different job sizes flow through because everything else is being backed up behind it. You're not properly blocking out for many. You're only blocking out from one huge job instead of multiple. So what we found we can tolerate is about 10. so that's where we typically run. So the top 10 jobs in our system get reservations.
Related to this, I was going to ask, in your previous one about reservations looking forward, you mentioned earlier. Could you go over that again? I didn't get that. How does it that? You had a thought.
Oh, well, that's not looking forward. That's looking. It's looking at the current reservations, and how many nodes are draining. In other words, they're idle but are blocked from running something because they have a reservation on them. And the other stuff above it is the reservation. So how many nodes worth of runtime or worth of jobs are waiting in the queue.
And the interesting thing there is how many jobs are reserved waiting for it.
That's some of it, yeah. So this happens to be the top 10. These are all XE jobs. We actually do 10 XE and 10 XK, so there's 10 for each reservations. And I don't know why the top 2 don't have a reservation. That's another bug we've got. So although those should have reservations. This is the bug. Sometimes we have to restart Moab in order for it to pick up reservations for a couple jobs. That's a recent bug, but anyway, so most of our jobs run are reserved based on node size. So the bigger the job, the higher the priority. there's a lot of variance in the node size, and that really affects how the schedule can flow things through. So there's ones that have reservations are anywhere from 5, 12, to 10,000 nodes, which affects the thrashing of the scheduler too. All right, back to where we were. So one of the other things that we do, and I mentioned this in terms of Jenkins, but Jenkins is able to run things that are user accessible. So it's coming in through a login node. So one of the other things we do is run on service nodes, at least a node in every class that actually mounts the file system. We run another test that's similar to what I was doing with LS. This one actually is like a 4K write, and actually this particular test, we actually have it set up to do a small write to every OST on the file system. So we're looking at response on every OST, on every file node of every class. So we don't do it for every node, but we're talking about 4 or 5 different nodes. Run these tests. They run them every so often. We try to, you want to run them often enough, you catch something, but not so often you're actually impacting the performance of the file system. And we plot it over time. This happens to be a multi-month plot where we can see we had a lot of problems in February. There were times when the response time spiked up, and this is average time in seconds. So this is averaged up into the 25-second range for getting response times from doing simple writes on some of the OSTs there. This happens to be a plot that shows kind of diving down through the data here. So on the upper left, we see maximum response time of the file system. So we've got some issues here, some spikes where we're getting much higher maximum response time than we normally get. So then we need to dive down into it. So on the upper middle, we look at average, including kind of look at how widespread is it. This is over time again. Then we plot it by OST. So this, if you click on a data point here, you dive down into plotting it by OST, which is the storage targets in the Ulster file system. And we can see here we're seeing lots of slow response time across a wide range of OSTs. So something else is going on there. It's not just, sometimes it could be a single OST problem. It's like OST load, somebody beating on OST, that's certainly possible. And how many are familiar with how Lustre stores data? Few, not very many. So Lustre doesn't, users don't have to stripe their data. It's up to them to pick the stripe width for their data. For large files, that can be very problematic. If they don't stripe the data, they can actually fill an OST if they're not careful, or we're not careful. But it's also possible they throw a lot of data on a single OST, and then when they're beating on it with a large number of nodes, they make it slow for everybody else. So that can be a problem. In this case, that's not so much what we're seeing. We're seeing something more widespread. So then we want to look at, well, what's going on? So we can plot then the I/O activity across all nodes in the system. And we can look at, see where the node activity were. If we dive down in, we then figure out, this is a plot of I/O activity across all nodes. This is by compute node, basically. And we see there's actually only a few nodes there, and they're all doing I/O in basically the same pattern. So that indicates most likely this is a single job that's causing this problem. And so then we go and identify the job and look at its individual write rate, which matches the overall write rate. And so now we know we've got a culprit. We can go talk to this user and say, what were you doing? What were you doing that will cause this sort of activity? And don't do it again, please. Sort of thing. So this is the sort of data that we're looking at here. This is another way of looking at it that looks at how frequency of data makes a difference. So this is kind of a normal plot of the I/O. This is a plot when there was some sort of problem in one of the storage targets, and there should be 2 identical jobs. If you didn't have the right frequency here, or a small enough frequency, you might not see this behavior at all. You might just see more of a line because it would average itself out if you have a longer frequency. So some lower resolution is often useful. You can also see with good resolution, you can also see more of the spiking behavior of I/O in the system, such as the write behavior from a particular job, which can be important to know. This is a little bit of a look at how we use this data to develop the answer to the question of, is the topology aware scheduler a good thing for us or not? Because when we put this together, this is sort of what the torus would look like for an average job mix pre topology aware scheduler. And it looks nice and packed, but you can see note that similar color means that this is all the same job. There's kind of sprinkled all over the place. That's an artifact that when you first start up a CRAE, it would pack stuff in quite nicely because it would give you a nice compact list. But as jobs start to stop and are different sizes, the open nodes start to get fragmented and spread across the system. And the CRAE would say, that's fine, we'll just go ahead and pack the job in there anyway. And that leads to, over time, fragmentation of jobs into larger and larger, more distributed things. And that means that communications now are spanning much larger portions of the torus. You have a lot more pass-through messaging, which is going to generate a lot less consistency for a single application. And you're also going to slow the application down, obviously. So, sorry. So instead, what we're doing is something more like this, which I showed a little bit of the data view earlier, where we're insisting everything to be a rectangle, a cuboid sort of shape. And that forces not necessarily minimal distance, but it prevents a lot of pass-through messaging. So in this particular job, this is small enough that there's not going to be any communication outside of this block, because there's no path that goes this way that's shorter than the path that's inside there. So that's a useful thing. The question is, this is going to have more unused nodes than this. Obviously, you're putting a constraint on your scheduler there, so you're going to have lower utilization. And as many of you that run computer centers know, the one metric that's easy to get and easy to present to your funders and your users and everybody else is the node occupancy. What percentage of your nodes are busy? Are they busy effectively or not? That's not the question. Is there a job assigned to that node? That's all that anybody wants to know, right? So that's such an easy thing to get that is and proving that this is better, it requires a whole lot more data. So that was why this was a hard thing to look at. So
it's also a trade-off, right? Because with everything is spread across, you're getting unstable performance, and maybe even slightly worse performance. But if you're packing everything nice together, the performance is good, but the jobs are waiting on.
That's potentially correct. Well, you can argue it both ways. They might not be waiting longer if the same amount of work takes less time to complete. Then yeah, exactly. So that's the argument. Yeah, exactly. So let's see. So we know the node occupancy is going to decrease. There's no doubt about that. It's hard. There's no way this guy can keep it the same way because you're imposing constraint on the system. You're going to probably the observation that we had was that we actually did see the expansion factor increase, actually decrease. Problem is, of course, is that when you're talking about users, the user workloads are the same one day to the next. So you can kind of talk about averages over time, but it's hard to look at it completely the same. And we did do some where we did some artificial workloads to try to test this sort of thing, but it was not completely reliable. So with our artificial workloads, we were able to show actually 25 to 100% performance improvement for jobs. It's really quite surprising on some key applications. It of course reduced variability by a lot. And so basically we get with the compact keyboard shapes, we get basically nearly dedicated system level of variability across runs of the same job, which means that users are getting extremely consistent performance and consistent at the upper end of the performance level. So that's a good thing. But we also saw 15 to 18% reduction in node occupancy. That's improved a little bit over time, but that's what we saw originally. So the question was, does this make up for that? Do we get more science out of the system? When we looked at individual examples, you could show an individual example. With the topology aware scheduler, we got basically better scaling out to larger node counts because you're getting less contention as you scale out larger jobs. So that's a good thing. We also saw this was actual user workload, so it's hard to be completely consistent here because the jobs aren't necessarily identical. But over time, this happens to be QCD, so the QCD guys are pretty much the same thing all the time, so it's not that much variability. But we can see over time, pre-TAS, this is sort of the runtime of their jobs, and post-TAS, they're about 60% short. That was encouraging. This is great. How do we really prove something more than that? So we started to look at individual variances. We ended up analyzing over 43 terabytes, 5 trillion data points, to try to find this trend in this data that would help show us what was going on there. Ultimately, one of the things that we found that was very interesting, beyond pure project, we did project comparisons, system-wide measures. One of the ones that we found to be the most interesting was network injection. So network injection is basically API sending and receiving messages. So the faster an application is running, the faster they're going to get to those API calls, and the more higher the rate of messaging is going to happen on the system. So conversely, if an application is slowed down, it's waiting in the barrier or something like that, that messaging rate is going to go down. So the higher the overall network injection of the system, the more work is getting done. It seems like a fairly reliable approach to look at it. And that actually turned out to be a very interesting metric. So we looked at a number of different things. So the application runtime and consistency all improved. That's certainly not a surprise. Overall expansion factor for some did increase when we looked at a larger test set, and no accuracy dropped. But overall, when we started looking at network injection, we looked at initially we were seeing something like this on average, 2.57, and we moved up to 3.66. So it's a 42% increase in network injection. That's a pretty convincing number that we're actually running jobs with the system faster and getting more science out of the system. And so that was this is one of those cases where we finally found the right needle in the haystack to use to prove the point. Similarly, and it's not surprising, we looked at data that indicated that the number of byte hops, how far in the torus does data have to move. We see a very significant drop in the number of hops that data has to move. That's going to mean it's going to move faster. It's going to have less contention as well. So both of those, it helped us figure out, what was the reason, what's a good measure to show that we actually are improving things. This allowed us to actually convince our funding agent that, hey, we actually know what we're doing here. Even though we're not getting the highest utilization, we're actually getting more science out of the system. Now, we haven't managed to convince our other people with PRACE to use it as too chicken, but they more or less told us that. They just can't see going to their funding agent and saying we have less than 95% utilization or something like that. It's just too big a pill to swallow for them. So, of course, on newer systems where we don't have the 3D torus limitations of pass-through messaging, you don't have quite as big an effect, or certainly nowhere near as big an effect on the communication topology. So you don't have, topology is not nearly important in general, but for a Gemini system, it is. And so we thought that was very important to look at. Let's see, so we also, just have to show that variability is also very, very good as well. So before I finish, I actually moved through these much faster than I thought I would. We show a few other sorts of plots that we have here. So as I mentioned, one of the things we look at quite frequently are storage. So this happens to be metadata server load on our scratch file system. So this is live data. We set the time and that sort of thing, different parameters here. But one of the things we see a lot of when we have problems on a file system is the metadata load spikes. So this is these are critical. Usually things get, when the metadata load gets over 500, it's really critical. Things basically grind to a halt. And we started to even look at where we need to do a failover of the metadata server at that point. But we also look at utilization performance over time. So these happen to be the plots that are slightly off to the right here. Are the utilization of each file system, and then the plots on the left are the amount of data read or written in a day. So a home and projects that's fairly small, Scratch is a little more interesting. We can definitely see when we do purges, based on activity, so file system. But we have a reasonably active file system, so our kind of average day here, we read or write about 1 petabyte of data. Spikes are in the 3 petabyte range, so it's not too bad. On occasion, we have days that we get like 9 or 10 petabytes every single day. That's a fairly impressive turnover of data. Let's see. So I was also going to show a little bit more about these metrics. So some of the things we do here also is look at, this happens to be an Scratch open rate, so we can look at various parameters that are coming off the system. So this is from all compute nodes, the sum of the open rate. So generally speaking, you can see we have a fairly stable open rate of somewhere below 5,000 opens per second. Our system is capable of about 25,000 or so, is really as well as the rated rate. We actually get a little more than that right now. But, so as long as we're well below that, we're in good shape. But start getting spikes in the 15,000, 20,000 range, you start to wonder who's doing what, sort of thing. That can start to cause issues. So if we click into a particular spike, we'll see if this data is still in here. This was a couple of days ago. This is the challenge of doing a live demo. I was not. That's why I preloaded some of these, because some of these plots take a while to compute and to sort through the data if they actually compute. So I may come back to this. We'll see if it comes back in a minute. This is a similar plot looking at network injection. We see there was a spike here. Someone might drive into that and look at what was going on. Similar to network injection here. This is across. This is. I think this did this so that I clicked on this plot here. This dives in. So this is at a particular point in time. It shows all nodes in the system. So this is just by the node number essentially, from 0 to 27,000. And it looks at, you can see patterns here. So you can guess that all these that have this height network injection are probably all the same job. And you can kind of gather which nodes are together and which ones are not. So if you want to know who is causing the problem, then you would dive into this one. See who was doing what. So that's the sort of thing. Let's see if this one ever finished. Still chewing. I lost my other one. So that's the sort of thing we're doing. We have an interface somewhat like this to produce these plots. So we can pick by job number, by job name, by user, pull up a plot by those sorts of characteristics. Either specify from the job names, the time range, or specify it here, and then look at the different types of data that we can look at, anywhere from I/O rates to network rates. Those are Gemini's, and there's also CPU and GPU utilization sorts of data in here as well. All right. Go along here. I think that gets me to conclusions, actually, so I'm running a bit early. So hopefully what I've shown is it's certainly possible to monitor Centura and get an enormous amount of data off the system and still get insights into that data. We're not anywhere near done with where we want to be, and we're 4 years into our project at this point. So we'll carry a lot of what we're doing now into our next system as well, as many of you do as well, and hope to continue to improve. So things things that we're not doing real well like that right now, like some of the log analysis we may rehash. Partly that's due to not having the personnel to keep doing the research and development parts of it, which we hope to correct soon. But it's also a matter of making sure you've got time to develop while you're also trying to do the system. The analysis of the system data is, of course, a big data problem on its own. So those of you that are dealing with big data challenges, one of the reasons we're looking for a big data person to hire right now is actually partly to work on system data analysis, not just user support sort of position. It's also possible to get a lot of insights from the system. Sometimes those insights are into problems. Some of those are into much more deep questions about how applications are using the system. Can they use it better? Can we change how we design the system in the future to make use of small amounts of memory or larger amounts of memory or that sort of thing? Who's using the GPUs in the system? Do we have people migrating the GPUs in a way that we can make the future system more GPU heavy? That sort of thing. Those are big questions that we're trying to use this data to help answer. They won't go all the way to providing that answer, but they do provide a significant piece of it. With that, I'm going to end. I can certainly take questions. I certainly want to thank the entire Blue Waters team that did much of this work. Most of this is not my work. Mike Sharman is currently the guy who's doing a lot of this monitoring data, particularly the OLS stuff. He worked a lot with the Sandia team. I'm bringing it up and making work with Blue Waters. Tim Bode is another admin who's done a lot of work putting together the Jenkins test suite and that sort of thing on Blue Waters. And of course, our funders. Questions?
Have you looked at users wasting resources probably without being aware of it? Like requesting huge amounts of resources and only using a small part of it by making